Okay, so compartmental analysis is a slightly strange thing in that it seems like it would only be useful for wastewater engineering. Okay? So compartmental analysis is this thing. You have some pipe flowing into some container. That container has an outflow pipe that flows into possibly yet another container. You guys see these pictures on Facebook sometimes?
Yeah.
Like, which tank fills up first? Like, shut up. We'll calculate how much stuff is in each tank. So, if you have some kind of complicated diagram like this with labels, so let me label this one. This flow rate is 5 liters per minute, and its concentration of whatever is 0.1 kilograms per liter. This one is 6 liters per minute, and its concentration is 0.2 kilograms per liter.
Wait, is that the density of the flow rate?
So that's a flow rate and a concentration of something. Right? It doesn't really, for the purposes of the idea of compartmental analysis, matter at all what the something is.
So flow rate plus density.
Yeah. So these are on, and why don't I have densities on these ones?
Same as the others.
No.
Oh, because you're not describing the liquid coming in. That's just the size of the hole, basically, right?
Yeah, this is really just the rate at which stuff leaves this tank, right? The concentration of stuff leaving this tank is going to be the concentration of stuff in the tank. You guys see that?
Wouldn't the viscosity matter, though? Like,
No. Let me add an assumption. Oh gosh, that's not how you spell assume. Assume well mixed.
And unsettable.
Yeah, well mixed.
Assume ideal conditions.
Assume the ideal conditions. Assume that you have salt water and water. That, really, I kid you not, every one of these problems so in every single differential equations textbook in which I have looked, the first compartmental analysis problem is always about brine being mixed with water. I do not know why. It does not have any relevance that I'm aware of. But for some reason, all of these problems start out with salt water being mixed with fresh water. Damn it, I just thought of relevance.
estuaries?
If you work at SeaWorld, this is extremely relevant. Okay, but anyway, so I have some flow rate with a concentration that's going into this tank. And then that same flow rate happens to be leaving this top tank. So my question to you is the level in this tank changing? You guys see that? No. This one is...
Have a level, would it? Wouldn't it just, the same amount going in would just flow?
So if I started it with some in there, right?
Okay.
Then the same amount would be in there. You guys with that? If I start this one with some amount in there, what's the tendency going to be? It's going to rust, right? Oh, and I didn't label that one. That one's supposed to be 9 liters per minute. Okay, so if I start this one with... Well, obviously it drains out the bottom. Don't be silly.
That's the bottom?
Yeah, the arrow pointing towards the bottom then?
It's confusing.
These arrows are pointing into the tank. This tank is obviously disoriented this way.
Okay, so how do you explain those first two R lines?
Jeez, dude, it's a picture. Okay, fair point. So if I rearrange my picture slightly.
Well, you're also going to have to erase the bottom line.
This one?
No, the left, yeah, that one won't be rising.
It definitely will be. It's getting 6 liters in and it's only having 5 liters out. It's definitely going up at the same rate. All I did was make instead of having a square tank, I now have a square with a panhandle tank. Like, who cares? For real, it's the same picture, I promise. Now, is this one tending to fill up or empty out?
Well, we're putting in 11 and we're only getting 9 out.
No, you're putting in 10.
I'm putting in 10.
Oh,
And I'm taking 9 out, so it's gonna fill.
what's the pressure on the, because you connected.
No, yeah, we're ignoring pressure. This is all about the amounts of salt in the tanks, right? So this is, and the way these problems are normally phrased is you have some tank that starts out with X salt water in it, right? And you have some inflow rate and some outflow rate. So the very first thing I want to do is just truncate a bunch of this picture and consider just one of these guys. So I'm just going to look at this one first. Right? And I'm going to assume that it's, I don't know. So I'm going to add some assumptions. I'm going to say it starts with X kilograms of salt. Oh, what the hell. I'll just do it. We'll say it starts with 0 kilograms of salt in 100 liters of water. Cool. Now, I think you guys have already kind of intuited the governing differential equation here. What is the thing you've been using to tell me that the tank is either staying with the same amount of stuff or getting more stuff?
That'd be like acceleration almost, right?
Difference between the rate in and rate out.
Yeah, you're just doing the rate of change of stuff in the tank is the rate in minus the rate out. You guys with that? So like that's the punchline of compartmental analysis is it's rate of change is rate in minus rate out.
So delta,
Yes.
so delta V is equal to VI minus VO.
Yeah, exactly. So in the volume land, right, the change in volume is the change in volume in minus the change in volume out. Right? Okay, now the other punchline of compartmental analysis is that you do not want to model the volume of, you do not want to try to write a differential equation for the concentration of anything. Okay? I'm going to add that to my, do not try to write a differential equation for concentration. Write instead a differential equation for rate of change is the rate in minus the rate out. Okay, now that gets weird, right? Because the concentration I want is something about, like, what's the question I should be asking for this? If I start with no kilograms of salt in 100 liters of water, right? So I start with 100 liters of pure water, and I have this tank where it flows in at 5 liters a minute. That's got a concentration of 1/10 of a kilo of salt per liter, and flows out at the same 5 liters a minute. Right? You guys with me?
If we assume well mixed and it like instantly mixes perfectly, it's never gonna actually be pure salt water, right?
Yeah, it'll never be pure salt water. It'll never get, well, it'll be salty water, I guess, instantly, right? As soon as some little bit gets added. but it will never get to what?
0.1 kilogram per liter.
Yeah, it'll never get to the concentration of water flowing in, right? Because there's always going to be some kind of residual effect of the fact that you started with pure water, right? What will it tend to do?
Approach that as you mentioned.
Yeah, it will approach that value, of course. You guys see that? Okay, so the thing is, I want to know, the question I want to know is, write a function for concentration in terms of time. Does that make sense? Like, that's clearly the goal I should be after. But I just told you, don't try to write down a differential equation for concentration. So, if you can't write down a differential equation for concentration, what do you write a differential equation for?
Volume is a function of time.
Good. We could write a differential equation for volume as a function of time. Here, I'll write that one over here. In this tank, right? Same rate in, same rate out. It's all you guys told me it was always going to be the same. And if I said it started with 100 liters, it's going to be 100 liters all the time. This one down here is different, right? So I kind of made fun of you for that, but that's actually a good thing to do. You're going to need that. In this case, it's a constant function, so it's pretty chill. In other cases, you're going to have to figure out what that thing is. Cool. So get a volume function. What else?
We should try to figure out at what rate is salt leaving the tank. Well, we know at what rate it's going into the tank.
Yeah,
5
so
liters per minute and 0.1 kilogram per liter. You crank up the
okay, so I think I want to do this equation, right? Rate of change is rate in minus rate out. Not for concentration, but for
kilograms of salt.
kilograms of salt. You guys see that? So the key is you don't write a differential equation for concentration. You write a kilogram, or you write a differential equation for the amount of whatever it is. Like the raw stuff that's dissolved in the water. So you imagine pulling the water up, throwing it away, what would be left?
We would multiply those, right?
So we'd say, all right, I'm going to let x of t be the amount of salt. Right? So that's going to be the amount of salt in this tank. I think you know about x of 0. What was x of 0?
That's 0.
0. Why is it 0?
There's no salt being.
Because there's no salt in that water at the beginning. Right? Okay, and then what's the rate of change of the amount of salt?
Half kilogram per minute. Right there for the top one.
Okay.
Wouldn't it be 0.5?
Oh, nice. Right? Because this is the, I know that's what he said.
Okay, I was like,
I wanted to do that in 2 steps. So that's the amount of salt you're getting from the input pipe, right? So it's 0.1 kilogram per liter, yeah, times
5 liters per minute.
5 liters per minute. So we're going to get half a kilogram per minute coming in. What's going out? Uh-oh. Okay, how about the left-hand side? What's that?
Are you just doing this for that first tank?
Yeah, I'm just doing this first tank up here. You can forget the other 2 for a minute.
So that's going to be 5 liters per minute times whatever the concentration of salt is in the tank.
Okay. So definitely the flow rate is 5, right?
Yeah.
And all of these are going to be a concentration times a flow. And this guy's a flow on, I don't know why I wrote this backwards, but that's a flow, and then this should be a concentration. Okay. And what am I modeling the rate of change of? Like,
The concentration of salt in the tank.
no, close.
Or the amount, yeah.
Yeah, total amount of salt. So this is going to be x prime, right? Now we have this weird question of, okay, so obviously the first little bit of water flowing out basically doesn't have any salt in it, right? But then what? Yeah, then it like has some salt, and it gets mixed around, and then some of the salt leaves. So it's not always getting more salt, right? Because some of the salt that it got is leaving.
Would that last one be like a linear function of time?
Close, kind of, maybe.
Is it x divided by the volume of the tank?
Oh yeah, I mean that's kind of how you would figure it out, right?
That's the function.
Should be, you take whatever volume there is, divide by that, and how much salt did you have?
X.
X. You guys with me on this? Cool. All right, can I solve this? I think I got x prime is 0.5 minus x over 20.
First order separable?
Yeah, that's separable. Right? You can even multiply it through by 20 just for kicks. Anyways, you guys can solve this, right? Okay, so I'm going to assume that we can solve that and get x of t. What's the form of x of t going to be? Yeah, there's going to be some kind of exponential thing in there, right? And what's that exponential going to taper off to? Yeah, it better go to 0.1 kilogram per liter in the long run. Keep in mind, this is x, right? Which is the total kilograms of salt, right? So if you want the...
We just divide by 100 too.
Yeah, if you want the concentration, you need to divide by 100 from that. You guys see that?
And that's the total amount of salt that has left that after a certain amount of time? Like the
No.
salt that's coming out of it, or how much has gone into it?
That's like if you put gates on both ends, just dropped them in all of a sudden, and then dried all the water out of that. That's what x of t would be.
At a specific time?
Yeah.
Okay.
So that would be the time at which you drop those gates in and evaporate all the water. You guys cool with that? Okay, so let's see if we can write differential equations for the other two while we're kind of sitting here. Okay, so I'm going to call this tank X. What are you going to call this one? Boring. Y. What are you going to call this one? Super boring. Okay, so we found that X prime was 0.5 minus X over 20, right? Okay, what's Y prime?
Is that a 0.2 kilos per liter?
Yep, so that's 2 kilograms per liter coming in.
Oh, 2.2
kilograms per liter, sorry. 2 kilograms of salt probably won't dissolve in a liter of water. Right?
Probably not.
Not volume, yeah. I'm assuming that volume's... It's an interesting question. There must be a limit to this, right? It depends on how warm the water is, though, right? Is there another limit after you heat it? Anyway, whatever. So, point is, how much salt's coming into this tank?
Multiply those two.
Yeah, you multiply the flow times the concentration, right? So we're getting 1.2 kilograms in. And then how much are we losing? Did I lose you there?
1.2.
So this should be
Oh, okay, you skipped.
should be a flow times a constant. So flow in times concentration in, and then we're going to subtract flow out times concentration out.
Did the initial 0 kilograms of salt in 100 liters of water, did that apply to all of them, or was that just for the first one?
That was just that one. I was just fiddling with it. It won't matter in terms of writing the differential equation.
Okay.
That was just going to set my constants at the end there, but I didn't bother to solve it like a jerk.
So that would be the 1.2 kilograms per minute.
So the flow in was, 6 liters per minute, right? And then the concentration was 0.2 kilograms per liter, which is indeed giving me a rate of change of salt with respect to time. Right, that's kilograms per minute. That's what you would get from differentiating kilograms of salt with respect to time. And then how about your flow out?
5.
Okay, the flow out's pretty easy. It's 5. And that's in liters per minute. And then the concentration out's harder.
It's going to be Y divided by whatever the volume of the tank is.
Yeah, so that's going to be Y divided by your volume of your tank, right?
Volume
Which
is.
increases 1 per minute.
Yeah, and I didn't tell you how much water was in this tank to start with, right? So let's assume we had the same 100 liters. So this tank is special because,
It's filling up.
Gaining 1 liter per minute.
yeah, it's gaining a liter a minute, right? So your concentration's Y kilograms per, how many liters of water are in there?
100 plus T.
100 T.
Yeah, whatever there was to start with, plus T.
Because of the 6 minus 5.
Yeah.
Should we account for some sort of upper limit, the fact that that tank is increasing, but it can't increase indefinitely, there's a finite volume to that tank?
Yeah. So we probably should make some domain statement about this based on how big this tank is.
We don't really know that, do we?
Yeah, I didn't give you that information, so that's a good concern to worry about, right? Okay. Punchline of this? You guys want to enter linear algebra land with me?
So, no.
Okay, so no, you'll be fine. Just chill. Don't worry, it's okay. What's Z prime?
It's a function of X and Y.
Uh-huh. So what's the amount of stuff coming into the Z tank?
Is it the solution to that system when it's X and the out of Y?
Okay, so it's getting the out of X, which is minus X over 20, or X over 20, right? So it's getting the out of X and
The out of Y.
the out of Y, which is
5 over
5y over 100 plus t. Right, so it's getting 2 n's, and then it also has a minus 9 times,
Z over.
good, there's a z on top, and on the bottom there's, oh, I didn't tell you how big that tank was.
What else on
Let's assume it's a 200 liters to start with.
200 minus. Yeah, T.
200 minus t?
Plus.
Plus t. I think the volume's getting bigger. But if it was getting smaller, right? If we had 11 liters out, we'd do minus t. You guys all see that? So this thing looks like a nasty little critter, right? Here's z. Except that we could actually do this right now. with the techniques you have, you could solve this. You don't need linear algebra. You could solve x and solve y and cram those in for x and y, right? And then you'd have some kind of non-homogeneous, horrible thing. But you could solve it. Would it take you a while? Probably. Would it take you eternity? No. It might feel like eternity while it takes you an hour to crank through it, but you could crank through it. So what was the punchline of compartmental analysis? So the punchline should be this thing. Rate of change is the rate in minus the rate out. And for rate in, you might think flow in times concentration in. For rate out, you might think flow out times concentration out. And do not try to write a differential equation for the concentration. It will not work. Also, note at the end, the thing you have obtained, right, when you solve for x and y and z, those are not the concentrations of salt in the tank. Those are the amount of salt in the tank. If you want the concentration, you need to divide by the volume of the tank.
Could we do Gaussian elimination on a matrix with this?
Sure, I'll teach you how to do that later. It gets a little weird here because you have differentials, right? But yeah, we can do some kind of matrix techniques to solve them. Yeah. Okay, cool. Questions, thanks?
You want the quiz?
Okay.